Hey everybody. Um, After thinking about posting solutions or answers, I guess, to the first homework assignment here, I thought that maybe what might be most helpful is for me to actually just kind of run through the assignment, show you what you're supposed to do for some of these. I'm going to pick and choose because I don't have a lot of time. Still need to get ready for lecture later today. But let's go through this, and I'm going to emphasize kind of like what's important to me and maybe what I think people are possibly confused about, right? We'll talk about number one really quickly here. So you have the formula, right, for the gravitational force. All you needed to do is write something like this, is that the electric force, we said what, between two electrons is going to be k e squared over r squared, right? So when you take the ratio here, what you'll find is that the r squareds cancel out, right? And you also need to note that the electron has a mass of like 9.11 times 10 to the negative 31st kilograms. You also need to know, the Coulomb constant and the fundamental unit of charge, E, in the universal gravitational constant. But if you have all that stuff, it's just a matter of plugging the numbers in, and you should find, right, that the gravitational force is much, much weaker than the electric force. Number two, right, I kind of already said that I don't intend to test you on kinematics or anything like that, but so I'll just talk really quickly about what you wanted to do here. You wanted to write that let's say the magnitude of the electric force is QE, right? And so then what we find is that if actually, let me just write this. If we find that the only force we're considering on the electron is going to be the electric force, because we just kind of showed that the gravitational force in general is much weaker, then we just write that this is ma, right? So we can solve for the acceleration the electron experiences, and then we just kind of take this a and we plug it into this kinematics equation. It's like this. And I'm going to write minus 1/2 at squared, where I'm just going to take the absolute value of a, because right, thinking back to kinematics, this means that the electron is actually going to hit the bottom plate at some time, right? Number three is just kind of a math thing. I don't really intend to emphasize that, but you just want to remember that the script r is the separation vector, right? So you just take the r vector and subtract from that the r prime vector, and then I just wanted you to draw the x and y components. So that's that. Let's see, number four. This would be a good one to make sure that you're like pretty clear on. And unfortunately, looks like I'm gonna have to make a sketch here. I don't have a tablet. I might be able to talk to somebody about getting one, maybe. But so I'll just have to draw this in paint, and it's gonna be shitty, but that's fine, right? As long as it gets the point across. So it's a good idea, right, to sketch the charge distribution. I'm just going to put down like a y-axis real quick. Okay, it bothers me when I can't get these perfectly straight. Like that, and then put down an x-axis. Okay, it's not perfectly straight, but let's just go with it. So what we have, right, is we have, let's say, I'll use red for positive charges and another color for negative charges. So the first charge is placed on the x-axis, right? So like here. Okay, that's probably clear enough. I'll use blue for negative charges. And then the second charge is placed basically on the other side of the point x equals 0, right? So maybe it's approximately here. Okay, and then we have a third charge that is positive, right? So I said that I would make that red, and that's going to be down here, and it's a little bit further away from the origin than the other two. though that doesn't actually show up very well in the sketch here. But remember that like the electric field due to a positive point charge will point away from the point charge. It will point radially away. And the electric field due to a negative point charge will point toward the charge, right? Like radially toward the charge. And that's kind of all we need here, along with this kq over r squared thing. So if I were to just focus on the origin, right, and so this is kind of an instance of us not really needing that script R notation because we're just talking about the origin. I could say make a sketch, right, and we're gonna have, let's see, the electric field due to Q1, which is here on the right, and is going to look, you know, it's good. It's gonna look maybe like this. Right. Yes, I'm literally writing with my mouse. It's very painful. The electric field due to Q2 is going to point toward, right, the charge, and it will actually have the same magnitude as, will it actually be the same contribution to the electric field as the positive charge, the one we just drew, because, right, they have the same separation from the origin, and one is negative, but it's to the left, and the other is positive, but it's to the right, the charges. So we could draw this in like this, and we'll call this E2. And then E3 is going to be pointing straight up, again, because the electric field points away from positive charges. And we'll put that in red, and so that should look like this. If I could draw like a straight vertical line. Like so. And then you just have to take the vector sum here, right? And so I've gotten a lot of questions about this, so maybe I'll just elaborate on this really quickly here. But and I think what I would like to do is focus on, well, this isn't actually the best example of this, but I'll talk about it anyway. If we say like focusing on E2, right? I could write something like this. I could write E2, the vector, as being equal to K Q2 over, what did we say, A, right? Because remember that A squared. Remember that I always want this term down here to be positive, whether I'm talking about electric fields, forces, or potentials, right? So here it's kind of obvious that this will always be positive because we're squaring something, but even when we're talking about electric potential where there's no square in the denominator, we still want that term to be positive because it's just a distance when it comes down to it. So I could do this. Let me just double check the work or the thing here. So I called it Q2. Okay. So then this, right, would be, if I want to make it a vector, I'm just going to tack on an x hat here, like so. And notice, right, that if I substitute in what I'm given in the problem statement for the charge, I just write this. I write K and then times negative Q over A squared x hat. And the point is that this is directed along the negative x axis as we expect, right, for a negative charge. Alternatively, right, what I could do is just do something like this. And in this situation, it's kind of maybe a little silly to write something like this, but you know, it's still technically true. I could just put negative Q in absolute value and then put a negative sign out in front of the whole expression to also indicate that I realize that it points to the left, right, like this. And so this is, you know, when this is not so useful maybe when you're given something like the charge is negative. Let's say what we had was this, right? We had Q2 was negative Q. But contrast this with something like Q2 is, I don't know, negative 5 nanocoulombs or something like that, right? Then it's like this minus sign is wrapped up in what Q2 is. And this would be a situation where you probably want to put an absolute value sign around Q2 so you don't get a double negative and end up indicating that the vector points in a direction opposite to the direction it actually is supposed to point, right? So there's that. From here, right, it's all just vector addition, and we just add up the E1 and E2 contributions to the electric field in the x direction, negative x direction, and then we just have one thing contributing to the electric field in the y direction. And so it's just, it's just cranking that out, right? So hopefully that's clear, and I don't think maybe I really need to go any further with that. Let's see here. So number 5, lots of people had questions about this one, and they were good questions. And I think one of the biggest or most frequently asked questions was like, should I get something weird for the electric potential when I actually do this integral? And I mean, it's possible you got like arc cinch or something very strange, right? And that's okay. I don't think there's anything unphysical about that. And again, you shouldn't stress, like if you don't know the antiderivative of, or if you don't know whatever function's antiderivative gives you arc cinch, it's okay, because I'm not going to give you something like that on the exam, right? I'm going to give you, or if I did, I would just, I would give you the integral formula. So it's not a big deal. But for this one, this is going to be a good one to make a sketch for. And again, it's going to be a little rough, but let's try to just kind of get something down. Okay, so I want to draw this rod, which maybe looks like this. And it has positive charge. And then what I want to do, right, is I want to calculate the electric field, say, like at this point P right here, maybe. Now, I gave you these endpoints, in terms of relevant quantities, but you don't actually have to use mine, because what I think is actually better here is to say that this point here is at x equals 0. This point here is at x equals L, because this is going to make it so that when you write your r squared term, you have a nicer expression, right? So then what we want to do is the same thing as always, right? We just shade in a little bit of charge dq, right? Like here maybe I'll say this is dq, and this is at x equals x, and it has length dx. Right? So then with this sketch in mind, let me try to be better about drawing some lines here. I'll just draw the line that connects the bit of charge to where I want to calculate the field. So it looks like this. And then my electric field vector should look like this for that bit of charge. So we'll write dE here. Now, this line, right, that connects the bit of charge to the field point is going to make an angle, and we'll call it like theta with respect to the horizontal, right? This theta. And then this allows us to break the electric field, the infinitesimal bit of electric field, into its components. And we want to do this here because we don't find that there's going to be any kind of nice cancellation, right? That's what is sort of making this problem obnoxious. Now, I'm going to trust that if you see that this angle here is also theta, right? The angle made by this horizontal line that I'm drawing and the infinitesimal bit of electric field, that you can break this into its components, right? Its x and y components, and then carry out those integrals separately. But let's just like talk about what your r squared is here. So in this case, I'll just write a regular r because it's kind of hard to actually typeset that r quickly. So I'll say that like our value is this, and you should check this to see that it kind of makes sense, but it's going to be x squared plus h squared, right? Because we said that the point was, what did we say? We said it's h above the left end. Yes. So you want to check this, right? You want to check this at, I'll say check this for at least x equals 0 and x equals L to ensure it gives you what you'd expect, right? So there's that, and then it's just a matter of kind of writing out something like, let's do the x component, dE sub x is going to be k over r squared, and then we'll put on a cosine theta and then dq, right? Like this. So then from here, it's realizing that lambda being defined to be a charge over a length tells us that we can write something like this. We can write that dq is lambda dx. And then we just take this and we plug it into our expression above. And we also have to substitute for cosine, right? Remember, cosine theta is going to be adjacent over hypotenuse, so it's just going to be x over r, not r squared. I almost wrote r squared. It's going to be x over r, right? And then so what you have to do is you have to do like some things here. You have to substitute in what r squared is everywhere, or r rather. So this tells us, right, that obviously r is the square root of x squared plus h squared. So that would be like one thing we need to do. In particular to this, right, we need to plug in what r squared is. Then we need to plug in what cosine theta is in terms of x and r, right? And then we need to note that, again, that r is this. And then we need to finally write that dq is lambda dx. And then we just crank out the integral, right? And that's hopefully something that is not too intimidating or scary if you have the antiderivative formula. Oh, there's something I wanted to say. Oh, yeah. So your limits of integration in this case, right, would be x equals 0 to x equals L. You don't want to integrate beyond where there's charge, right? Because that doesn't really make physical sense. And also, I think I've said this to at least a few of you, if I didn't say it in class at some point, if there's a symmetry that you observe when you're doing a problem like this, then it kind of makes sense to try to make sure that your limits of integration are symmetric, i.e., here that would look like integrating from x equals negative L over 2 to x equals L over 2. But this is not symmetric, right? So you just want to look out for those symmetries and try to set yourself up for nicer limits of integration if they're appropriate, right? Now, the potential is almost exactly the same thing, right? Except there is one thing that makes it nicer, and that's that potential is a scalar, right? So we don't need to write anything like cosine or sine. So our potential is just going to be this, right? And then if we plug in what everything is, we get k over square root x squared plus h squared, and then lambda dx, right? Like this. And so that is this is all you have to integrate for the potential. So don't do two integrals, right? Don't write sine or cosine because potential is a scalar, and that's going to be something I really want to make sure everybody is good on. Like if you know nothing else about electric potential, that you know that it's not a vector. So then, yeah, you crank the integral out, you might get something weird, because I think that you can, maybe somebody who's more, adept at math, could tell you more about this, but I think that you can write these like sinh and cosh, or like arc sinh and arc cosh functions in terms of natural logs, and like vice versa. So, you probably will get something weird there, but it's okay. All right, let's see. What about number, was it 6? I think this is a good one. So I'll make a quick sketch here and just talk about what, we have to do. So again, I'm going to make some x and y axes. Okay, I think that's fine. Okay, there's that. Cool. So then these are my x and y axes. We have that there is a negative charge over here, say, at x equals negative a, right? Now, I'll just do maybe the electric field here, and then you can sort of see how you might do the electric potential. So let's talk about the contribution to the electric field that this charge will have at the origin, right? So if I just maybe up here, I say like, okay, let's think about the origin. The electric field, right, will point toward the point charge, the negative charge, like this, right? And we'll say that this is, we'll just call this E minus. Now, to get a cancellation, what we're going to have is that there is some other contribution to the electric field from a positive charge that looks, okay, that was bad. I'll try this one more time. I drew such a straight line for the other one. Apparently, I've lost my touch. Okay, let's all pretend that's a straight line. There is going to be some other contribution to the electric field, right, from some positive charge that has to look like this for us to get a cancellation. So that means, right, that means that this other charge has to be situated to the left of the origin. Because if the positive charge is situated to the right of the origin, we can't have an electric field that looks like this one that I drew in red at the origin. And again, this just comes down to this idea that the electric field points radially away from positive charges and radially toward negative charges. Okay, so we also need to think, and this is not super important, honestly, because it'll all kind of just work out, but we need to think about maybe where this charge should be. And I'm going to just argue that because the magnitude of the positive charge is 3 times as large as the magnitude of the negative charge, the positive charge should probably be like somewhere out here, right? It's got to be to the left of the negative charge. Otherwise, there's no way we could have this cancellation, because the magnitude of the electric field due to the positive charge is going to be larger than the magnitude of the electric field due to the negative charge. So let's just put some stuff down. We're going to say we know that this is at x equals negative a. And let's just say that this is x equals negative b, something like that. So then to write out our condition for the electric field being 0 there at the origin, and we'll just talk about the magnitudes and put signs in front, like SIGNs, in front of the contributions to indicate their direction, because this is just a one-dimensional thing, right? So we could write something like E net is going to be E minus plus E plus. And we know that E minus should point to the left So I could write E minus kind of any number of ways, and this is another good example of what we're talking about here, or what we were talking about earlier. So what I will do is maybe just write it like this. So this is something I could do. I could write KQ minus. Now remember, Q minus is negative over A, and remember that, or A squared. Remember that I want to make sure that whatever I put in the denominator is positive, and in this case it is because if x equals negative A is to the left of the origin, then that means A, as I've stated it, is actually a positive number. Now this points to the left because there is a minus sign included with Q minus, right? So this is fine. And then for the other one, right, this would be KQ plus over B squared, right? And remember, just from the problem statement, we want this to be equal to 0. So I'll show you another way you could do this, right, just to hopefully get this absolute value confusion kind of, settled. I could do this. I could write negative KQ minus over A squared plus K. Wait, what happened here? Let me fix this. KQ minus over A squared plus K. And then I don't have to do anything to Q plus because it's already positive, right? Over B squared. Yeah, so I think this is fine. The last thing to do, well, like one of the last things to do here would be to just substitute what these charges are. And then I can go back to this other notation, right? I can write minus KQ over A squared plus K 3Q over B squared. And then just remember that this is equal to 0, right? So all you have to do here is solve for B. And you should find that the K's and Q's cancel, right? Because we have this equation being equal to 0. Now, to talk about the electric potential, right, we could also write something like this. We could write V total equals V minus plus V plus. And this is going to be a little bit different because now, right, the electric potential is a scalar. And in this case, this means that we're going to want to have our positive charge to the right of the origin. So I need to write something like this, essentially. Minus KQ over A plus K 3Q over B, and then demand that this equals 0, right? So this might look like, if I just get rid of this, I don't know why I'm so set on getting it completely out of there, but I started and I'm going to finish. So what we'll do is we'll just put, now we'll say something like this. We'll say that here we have the positive charge now when we're thinking about the, damn right click, when we're thinking about the electric potential, and we'll say that this is now at x equals c. So let me change my notation because these b's aren't the same, right? And I want to make sure that that's clear to everybody. But remember that so the important idea here is that a positive charge will always make a positive contribution to the electric potential at a point, and a negative charge will always make a negative contribution to the electric potential at a point, right? And that is different from the electric field, and the reason is that the electric field is a vector and the electric potential is a scalar, right? So hopefully this is helping people, understand kind of the subtleties of these things a little bit more, and like why we might write absolute value signs in some cases but not others. Okay, so then I don't know that I really want to talk about... let's see here. Okay, so I don't think I want to talk about any of these circular ones, but what I can do, just so you can see what the solution or the answer should look like, is I can put links in Canvas just showing like a diagram with the correct answer if you're interested in seeing those. Because these are, you know, problems that are very canonical and are given to students who take this class or a class like this every semester. So, you know, there's any number of solutions out there for me to just share with you. And then the same thing goes for number 8, right? And kind of any kind of circular distribution of charge. This one, right? This one we decided we weren't going to do, or it was going to be extra credit. And the issue here was that you just had to write that R is actually 3-dimensional. It has components X, Y, and Z. And then if you do that, you just crank out the divergence of that field, and then it will work out to be 0. We can talk about this one too, because this is probably a good one to think about. Here, since we're talking about Gauss's law now and charge distributions and stuff, so what we have is we have that for the rod, the linear charge density tells us that lambda is going to be Q over L, or this L, right? But Q is unknown here, right? Because we're not given Q in the problem statement. So we'll see why that's important and what we do about that pretty soon. But we do have this is true, right? And this is kind of just saying if you could slice off some cross section of the rod, you would find that there's some charge enclosed in there, right? Now, but we also, you know, are told that the charge is uniformly distributed throughout the volume, so we want to figure out how to turn this into a volume charge density. And this is not so bad, right? Because the volume charge density is just defined to be a charge over a volume. Now, the charge in this case, we can see from our equation for lambda, is just going to be lambda L, right? We just multiply both sides of that equation by L, and we get Q. And then we just have to write out an expression for the volume of the rod, which is going to be the area of the base times its length, right? So it's going to be something like pi, let's see, I'll do this very methodically. It's going to be pi r squared times the length, right? This is the volume of the outer, say, well, this is the volume of the full rod, assuming that it's not hollow, right? So we have to subtract off the volume that isn't there because it is in fact hollow, right? Like this. And so you should find something like this works out to be lambda L, and then we can do some factorization here. We can write pi L over r big R squared minus little r squared. And we find actually that that the L's cancel, right? So it just works out to be this. And let's just do something here. We'll check the dimensions here and make sure that it works out to be what we expect. We expect, right, I'll just put this in words. We expect a volumetric charge density to have dimensions of charge over volume. And so remember that lambda has dimensions of charge over length. And down here we have an area, right, in the denominator. Pi contributes nothing to the dimensions, it's just a pure number. So we see that this does work out dimensionally so that we have a charge over a volume, right? And that's it. Okay, hopefully this was helpful. I wish I could go, into more depth and stuff here, but we're moving very fast through this class, and I still have to prepare some stuff for lecture today, right? I'm sure we're all very excited about that. But yeah, of course, exams tomorrow. Reach out if you have any questions. I'm going to try to make myself very available, and I hope it goes well for everybody. All right, I'll see you.